Hello, everyone. Welcome to the second extended workshop. Let us know if you can hear us okay and if you can see us. You can use the chat. Okay, so welcome to the second extended workshop, Pioneering Sustainable Scalable Battery Systems for the Future. My name is Catarina and I am project manager at Innova. So Innova is supporting the coordination of extended projects as well as leading communication and dissemination activities across the consortium. I'm delighted to welcome all of you, our partners, researchers, industrial stakeholders, and guests joining us today. And for those who may be new to extended projects, these initiatives focus on pushing innovation in the next generation of semi-solid state batteries, with a special emphasis on sustainability, safety, performance, and scalability. Today is very special for us because we are live here from CEA, where all the partners are physically together this week for our general meeting. So this is an in-person setting that has enabled hands-on review of prototypes and technical alignment for these next generation semi-solid state batteries. So in this workshop, we will present key achievements of extended projects. Bruno, the project coordinator, will do a brief project. Rémy from CEA will dive deep into battery design systems. Lisa Lu, also from CEA, will talk about design prototypes, and Bart from Flanders Make will also talk about these prototypes. So before we start, I would like to acknowledge AVESTA, our project coordinator, and the excellent collaboration we have so far with all the partners, advancing the extended, and we also acknowledge CEA for hosting us today. A reminder that the session today is being recorded and we will host a live Q&A at the end. So please feel free to submit your questions in the Q&A, okay? You can submit them during the presentations and we will take them at the end. And now to officially open today's session, I'm pleased to pass the floor to Lisa Lu from CEA. Lisa Lu, welcome.
Thank you so much, Katarina. So thank you. I will just say a few words as an introduction, and would like to welcome all of you to this workshop. We reach almost the end of the project extended, and as Katarina said, we are here at CEA all together for a general assembly, and are happy to show you some of the results and our advancements and where we are at today. So today we will discuss the status of our project and show you the latest advancements, especially concerning the technical solution of the BMS from CEA and the prototyping of our modules to go finally to the next steps, which will be the testing of our modules. So I think we can start right now.
Okay, so to start, I'm delighted to introduce Bruno from AVESTA, project coordinator. Bruno has a large-scale innovation management experience and leading vision on strategic direction behind the extended. So Bruno will recap our advancements and share key updates on extended projects. Bruno, the floor is yours.
Good afternoon to you all, and thank you for attending the workshop. I will do a quick recap of what have been going on during these last 30 months in a very short presentation. We have right now, since our last workshop, we presented what were the developments under the BMS, the thermal, the mechanical, and the safety aspects of extended, mainly presenting what are our breakthroughs and developments under this situation. It was an intense part, and probably it happened a lot of development since this last workshop. Sorry, there were a lot of developments, and sorry for the lack of image. We will share again the slides. We lost the presentation because what I'm going to say next is we pass from the very modules that we were developing right now to what we are right now putting. That is our main goal, the module or the battery pack for the semi-solid state advancements. And in this, all what we talked about in the last workshop about BMS and development under BMS, the thermal, the mechanical, and even the safety are going to be applied. And what we are going to talk today, it will reflect this progress since the wireless part, the system design, to how we are assembling this with the capabilities of our partners, and how we are going to test this battery pack to ensure that we are achieving our goals. And this was the quick recap. Probably we will invite you to follow us and to see our main developments or our final developments in the end during May or June presentation, that it's going to be our final event. But for that, now I will leave the floor open to my colleagues, and in particular right now to Lisa Lu.
Thank you, Bruno.
I'm sorry, to Rémy.
We are going passing to Rémy. So Rémy, also from CAA, is a specialist in real-time embedded systems for battery and fuel cell management. His expertise sits exactly at the intersection of hardware, safety logic, and smart control. So Rémy, we look forward to hearing from you. Go ahead.
Good afternoon, everyone. So I will share a little bit of stuff on the battery design system. Within the expanded project, the aim was to work on the modular and scalable electronics for mobile solid-state batteries. Within this project, we we designed three kinds of BMS with Lumency, Fraunhofer, and CA. The one from Lumency consists of radio frequency communication with printable sensors. The one from Fraunhofer consists of local EIS with wired daisy chain communication bus between both chip and wireless connection to the side of the bus. And both of them have been presented during previous workshop. And today I will introduce you to the wireless optical daisy chain proposed by CA and implemented at cell level. And one of the main targets was to propose a way to make able a centralized EIS using a distributed cell voltage measurement. And we will see in a few slides what will be the impact in terms of cost and effectiveness. The wireless optical daisy chain communication bus designed in the extended project consists of flexible cell-to-cell communication bus. Design is based on a master-slave communication bus with a master read-write request addressed to a set of slave registers. Each node of the communication bus propagate the signals in two directions. The request from the master node is transmitted to the next cell node, while its response is transmitted to the previous. Once the master has received all the response, a new request can be transmitted to the daisy chain, and the next reply from the master node will go to it. One can see that the request is transmitted to the node with a delay that depends on the node's position in the daisy chain. One can see also that this delay is directly dependent of the forward delay between two consecutive. Now we will consider the constraint of a centralized EIS. The impedance of a battery cell is significant parameters for modern battery state estimator. EIS of a battery consists of measuring the impedance using the voltage response of current excitation over a range of frequencies. basically between few hertz to few kilohertz. A centralized EIS consists of using a global current sensor and current excitation. Temporal accuracy between current and voltage measurements is crucial for two reasons. First, impedance depends on both the amplitude and phase of the signal response. The relation between phase accuracy and temporal accuracy is straightforward. But temporal accuracy can also impact amplitude accuracy. It can be estimated that for a sinusoidal excitation frequency of around 10 kHz, an amplitude error of 1% can be produced by a time jitter of only 160 nanoseconds. Now, if we look at our battery system using a wireless optical daisy chain, one can see that it is necessary to trigger simultaneous measurement of cell voltage with delayed request. As the BMS is located at the cell level, its manufacturing cost must be very low. For this reason, we have chosen to avoid using crystal in the design. The clock accuracy is then around 3%. With this clock accuracy, a delay of 20 milliseconds will result in a time jitter of up to 600 microseconds, which is unacceptable for a centralized EIS implementation. So we need to find a way to be independent of the daisy chain delay introduced by the length of the daisy chain. This is why the CA is working on a synchronization method within the wireless optical daisy chain communication. And we will see now how appropriate synchronization can be achieved. First, the optical communication relies on a UART signal combined with a periodic pulse signal at the same rate to produce an averted return to zero signal. Then the non-return to zero signal and the periodic pulse signals are combined to produce an amplitude modulated signal that is transmitted to the next communication. In the following note, two thresholds are used to separate the communication signals and the periodic pulse signal. Then the communication signal is decoded to retrieve the UART message, while the received periodic pulse signal is used to synchronize the internal signals of the receiver. In the case of a trigger request, the decoded message is used to trigger a timer with the delay desired by the master node and adjusted locally according to the node's position in the daisy chain. Can simply use the ID of the node. Synchronized periodic pulse is then used to regulate the timer, in addition to being used to encode the signal to the next node, and so forwarding the clock across all the daisy chain. The measurement error is then no more related to clock accuracy, and daisy chain length has all the nodes the same signal to regulate the timer dedicated to trigger the analog to digital conversion. However, measurement error depends on the determinism of latencies in this concept, and one can see a tolerance on the start event. One can see that a tolerance is possible because we use only the edge of the transmitted clock to regulate the timer. So we have the latency corresponding to the period of this signal. And for example, for 115 kilobits, this will lead to a tolerance of 8 microseconds, for example. So this is sufficient to compensate for the low latency introduced by a well-designed real-time implementation in low-cost AB microcontroller. And now for the results. One can see the jitter observed for 80 milliseconds of waiting time between two nodes. And we can observe jitter as high as 120 nanoseconds. which correspond to a crystal of which correspond to 2 ppm of error. That is really near to a calibrated crystal. And so we can see that the design system can be compatible with a centralized EIS using distributed cell voltage measurement through all-daisy chain communication. And I would like to invite you to take a look at the mockup developed for this study using a short video. Developed to test different steps of the system. One can see the transmitted signal from the master node to a slave node. In red, it's a clock that is carried across the system.
It's still running.
Okay. So on the top, one can see the communication frame based on the UART frame with 2 bytes of data for each frame. So we can transmit 16 bits. The yellow signal, one can see the result of the amplitude modulation of the signal, and this matches to the received signal from the next. And below is the decoded signal. And then we have the reply, the instant reply from the node to the master or to the upper node. And then the received message by the master. So here is a mockup developed at lab scale to work on the message propagation for several nodes. In this mockup, there is 10 nodes. And one can see the optical emitter. Thanks to the camera, we can see the infrared light. On the oscilloscope, we could see the 2 consecutive requests from a master node. For the first one, for example, asked for voltage measurement. And then one can see the activity of every cell node in the daisy chain. And here it's showing the direction where the node is listening. So we can see that the first node, when he receives the master request, choose to transmit it to the following node and then stay until he receives every transmitted reply from the next. And so when the master node received all the reply, we can send another request. We developed also a gateway to interface this system to a computer using a CAN bus, and we had designed also man-to-machine interface to display the result of the measurement carried by the cell, the nodes of the digit. Feel free to ask if you have any question.
Thank you so much, Rémy. So to continue, I welcome Lisa Garcia again, who leads the major R&D initiatives in sustainable energy and battery system innovation. So she will guide us through the design prototypes and what first demonstrated reveal about industrial scalability. So back to you.
So thank you for the introduction. Once that we have developed the technical developments, for example, the BMS that we have just discussed, and the thermal management or the mechanical integration in order to test them in module scale. We need to prototype them, and this is what we have done at CEA, or this is where we are at right now, because we are on the process to assemble the prototypes and to insert all the technical developments we have made in the first part of the project in order to test them. So the goal is to, as I said, once we have frozen the designs, including all the technical developments, the goal is to assess the feasibility and the assembly into a higher level, into a module scale here in our case. Our goal is to create a formalized assembly procedure in order to safely assemble the modules to send them for testing. Here you can see some of the equipments we are using for this process of the assembly. We use 3D printers for fast prototyping. We use also laser cutting equipment and both here laser cutting and laser welding equipments, especially for the electrical connections, so to assemble the cells between each other. And finally, we also have testing equipment. In our case, for extended, we only conduct pre-tests to make sure that the electrical connections are working, but the real tests are being done at Flanders Mix. There will be a presentation afterwards about the testing phase. I just wanted to show you here an example of welding process that we can do at CEA and that we did for extended, where we configured several welding techniques and welding parameters for the electrical connections. So here you can see the laser welded configurations that were qualified and chosen for one of the module assembly for the extended results and module. And on the right, you can see 2 tests that we have performed to qualify them. So traction measurement and electrical characterization after this welding process. And finally, I wanted to show you here the process that we are using for the assembly. So I have told you in the beginning that we need a frozen design. And once the design is frozen, in this case, a module, for example, then we manufacture the pieces and we formalize the process sequence. This is for safety reasons, that we know exactly which steps goes first and which equipment is needed. And in the case of extended, and you will see that in the next slide with the video that will come, we start with the cell equipment, where we introduce the cells in cell holders. Then we instrument these cells. Then we start the sandwich assembly, which you will see in a moment. Then goes the welding process for finally reaching the final integration and have a module. And as I said, we do some small functional tests at CA only to make sure that the electrical connections are working. And then we ship and send these modules for performance testing at Flanders. So in here, you can see a video to show you exactly what it looks like for our, in our case, for the extended module. So you can see the first steps with 3D printing parts for the mechanical assembly. So at EA, we are able to print, to 3D print every pieces for up to module assembly. Here you can see the usual steps where we first 3D print the resin, and then we have to clean the pieces properly to remove the wires that are only needed for the printing process. You can see here that the technician will clean the piece. And this here you can see the cell holder that was designed for extended to contain the cell. And also here it's the configuration for CA to be able to insert the BMS and to have the proper connection with the cell. Here you can see the next steps that we have to go through, where we measure, we characterize the cell. You can see how it fits. So the cell holder was especially designed for this cell. So we ensure also that the cell fits perfectly in the cell holder. Then we use the laser welding equipment that you can see here on the right side. And you will see in the closer zoom here what it looks like. So this welding part was also especially designed for this cell assembly module, this configuration. For further assembly, we insert the gap fillers. So they are foams that will come in between cells. And in order for them to assemble them in a sandwich way. So here you can see some cells already assembled on the left side, and here we assemble a next one to form a module. The mechanical parts here that you can see are compression plates, as the cells need to be compressed. Because during their life cycle, they will their volume will change. Here we come to fix this assembly to make sure that it's stable. And now we are going to weld the tabs together to ensure the serial connection. So we are going to use the same laser welding equipment with a different, also qualified, standardized welding method that was developed on purpose for extended. So here you can see one example, but we connect all the tabs, of course, together. And we weld them. So this process is very fast. This welding techniques was qualified with different tests, with the traction test and the electrical resistance measurement to make sure that it's properly done, stable. And here you can see what it looks like. So it's in the round shape. It can take the form of different shapes, but here is the shape that was chosen for this project. And finally, we can insert, so the technical development that was introduced to you just before with Rémy, so the DMS that was developed from CA, we come to insert the card in the space that was especially created. And you can see, thanks to the first welding that was done, that the contact is properly done as we see the light. And finally, we come to check in our climatic chamber if the electrical connection is properly done, to check if the basic measurements of the module, and to see if we get all the contact that we need. Here we close, as it's a climatic chambers that is done to control thermal runaway, if in case there are thermal runaway. Make sure that we test this in a safe way. And then we move to the presentation of Flanders Made with Bart for once that we are done with the assembly of the modules, they will be shipped to Flanders Makes for testing.
Thank you, Lizalou. So from design to real world validation, testing is ultimately confirms feasibility, reliability, and safety. So please welcome Bart from Flanders Make, expert in industrial testing, validation, and product safety frameworks for battery technologies. Bart will share test plans, validation approaches, and performance insights developed collaboratively with our partners and especially relevant to this on-site working session at CA. So Bart, the floor is yours.
Okay, thank you for the introduction, Regina. So we'll continue to the test sequence we are going to perform at Flanders Make. So we have several test cases, which are divided in three parts. So we have the commissioning tests, we have the module test, and then the aging tests. And I'll go into more detail in the coming slides. So first off, I want to explain somewhat of the equipment that we're using at Flanders Make for testing and validation. So we have the high voltage battery module and pack setup, and this is used to test and validate the battery packs and modules, of course, using several types of tests, so CC, CP, CP, HPPC, but all different tests are also possible because this equipment is fully programmable and can be adjusted according to what we need. Then we have a liquid conditioning system, and this is a controlled heating and cooling setup where you can control flow and pressure of the liquids. Several liquids can be used, but this is then used in this case to cool our modules using the cold plate that's present in the module and then cooled via this setup itself. Then we have the real-time control monitoring safety setup. This is a real-time PXI and to perform all the measurements and control of the device under test. Especially on this side is that we have several safety layers. So we have a redundant shutdown mechanism which can be used in case something goes wrong. So the BMS itself is not only communicating with this setup, but also with all the other devices like the module tester itself with the conditioning, that if something goes wrong, all those devices can shut down the systems. And then last but not least, like also mentioned by Lizalou, we have a testing environment. This is a climate chamber, which is especially made for these kind of battery modules to eventually define the environment, so regulating temperature and humidity, but also again an extra safety level because you're putting the module inside there to make sure that if anything should go wrong, that it's still contained in some kind of container itself. Then the modeling and testing setup in more detail. So like you can see on the image above here, it's a mock-up image, but you can see that the module will be placed inside of the climate chamber, connected with the electrical wires, normally also the BMS wire, but you cannot really see them, and then also the cooling setup here. And it's again to create a controlled, stable environment according to temperature and humidity, and also as a safety measure. Cooling will be provided by the liquid conditioning system, like already mentioned. Then the battery module BMS will be powered by a low voltage supply, which you can see here. So we have the voltage supply of the battery module itself. Then you have the discharging and charging, all the different profiles, which will be done here by the module tester, which is all connected to the e-stop test and all other devices. The control system, like mentioned, our PXI real-time setup, which will control the module tester, but also read all the values coming from the battery module via BMS and then via a CAN system, and also a logging system. We use a CAN logging system here. Why? Because all the communication that's going to the control, to the module and so on is via CAN, but also all communication with the module itself and the BMS in this case is also CAN data, so that we have an accurate idea of what's happening, synced with all the data that's being transferred between all the systems. And then, of course, again, the liquid conditioning system that makes sure that the module is being cooled via the cool plate itself. Like mentioned, so the whole setup is controlled, checked, and logged using CAN communication. And we again mentioned there are several layers of safety to make sure that nothing goes wrong. And if anything should go wrong, that we can react as soon as possible in this case. Then for the different tests, so first off, we'll start with commissioning tests. So we'll do a capacity test to verify if the performance is up to par, to see what's normally the capacity of the cell. This is combined those cells and see if the capacity is what we expect from it. And then we will do an HPPC test to derive the internal DC resistance, the OCV, the polarization, and many other factors which you can find there by means of several current pulses. So what we do exactly there is we give them several pulses of certain amp level for different SOC levels. So you go with 100% SOC battery full, and then per step of 10%, you lower its SOC and you emit several pulses there, and you observe and analyze these pulses. And in this way, you can see what the internal resistance, OCV, and so on is for this kind of battery pack. That's the idea. Then going to the module tests. So what we're going to do here is charge and discharge at several C levels to see the influence on several parameters. And those are the capacity, the temperature of the module cells, and the pressure buildup. First of the capacity, if you charge at different C levels, you'll get a different capacity. So we want to see what the influence is on this C level on the capacity. Also a temperature buildup, because of course, if you charge at higher levels, you'll get a temperature buildup. You'll also want to see if our cooling system is sufficient with a cold plate. And then also the pressure buildup, because if you charge them, the cells will expand. So we want to see what's happening there during charging and discharging. Going to the module test, the second one is the bus profile. So it's a realistic consumption profile of an electric bus. And this one is a reworked version of the cell level to module level. So what we're going to do is to emit this profile on the module itself and see how many cycles it can go through. So for example, I don't know by heart which amount of kilometers this is, but if you run this cycle, there is a comparable amount of kilometers that the bus could run with this cycle. And then if you can go through this cycle several times, you could calculate how far a bus could ride with this kind of module or this kind of a battery pack. The same is also for an EV profile. So again, we will emit this EV profile, which is also a reworked version from cell level up to module level. And we can then, by running this profile several times, see how this battery reacts and also what the amount of kilometers would be if you would use such kind of a battery pack in your car, in your future car, of course. Then going to the final lists of tests. So we have the aging tests. These can see reliable aging quantification in lithium-ion battery modules. And it's very important to see how long they can live, because modules degrade over time. They have a capacity loss and the internal resistance increases, like you can see in the graph. In time, you'll have a capacity that lowers down and you have a certain knee point after which it goes down quite quickly. Again, the internal resistance does the same, but then it rises. Aging is influenced by the amount of cycles, the C rate, the discharge of depth of discharge, and temperature. So these are things we want to look at. But because you're working at something that's a module level, it will get more complex because you have cell-to-cell variations, you have balancing issues, thermal gradients, and system level interactions. So aging cannot just be scaled from cell to module base. That's why we're also going to perform these module tests itself. Aging tests use checkpoints, so your cycle count and amount for performance assessment. So you have first a baseline, and then you have a periodic evaluation of the module performance. So in between certain cycles, you're going to see what the capacity is. You can maybe also perform HPPC tests or a test to see how the cells, and in this case, the whole module, will evolve in time. Development of aging modules linking performance decay to stressors. What we mean by end of life is what mostly used is if the sensor, the module reaches a state of health of 80%, and this means that you have about 80% of the beginning capacity in your cells left. That's the idea. And that was about it from my side.
Okay, thank you, Bart. To conclude our presentations, we return to Rémy and Isabelle, our hosts, who will together give us the findings and outlines and our next steps. Very quickly. So, Rémy and Isabelle, thank you.
So next step, we need to finalize the CA version of the BMS and to gather other BMS parameter to connect to Canvas, where the result, and then to transmit the system to design for the functional validation.
So yes, so for the next steps, as I said also before, we are still in the process of receiving the pieces for the assembly of the modules. So once we receive all of them, we can process with the assembly steps, then validation, pre-validation, and then shipment and sending these modules assembled to Flanders Makes for their testing and to validate our KPIs and objectives of the project. So thank you a lot for listening, and do not hesitate if you have any questions.
Thank you both. So floor is open for questions. I'm not sure if you have any question. Let me check. Okay, we have one question. So Xavier is asking, I was wondering how robust the optical communication system would be in working conditions where vibrations are present on the module or the surrounding air is not totally clear. Yes, sorry.
So, regarding the vibration, PCB is really small, so it shouldn't be so much affected by the vibration. The slotting section is designed to fix the PCB great amount of friction. And regarding the air dust, for example, or quality of the air, we can use the hole in the cell holder that is used to propagate the optical signal to put an acrylic pipe on it to join optical emitter to receiver. And in this order, we can have a system completely close to the dust or the and this can also help with increasing the signal to noise ratio. I don't know if it responds to the question.
Thank you so much, Rémy. We have another question for you from Jen. So he says, hello, reducing the daisy chain delay from 600 microns to CA 80 microns sounds great. How big is the impact on performance and aging of the model?
Sorry?
Yes. If any other of the speakers wants to answer, as well.
Regarding the pressure sensor, it's more related to the work, and the idea is to compare the pressure measurement during the complaint aspect with the EIS extract local integrated circuit implemented by Fraunhofer, and it is to correlate the EIS measurement. And additionally, we add another kind of pressure sensor in the CA version of the BMS with an external to be attached to the body cell, and it will be pleasure to compare the result between the kind of pressure. Yeah, so it is to monitor the pressure evolution during the usage of the battery and not just during the battery aspect.
Thank you so much, Rémy. So we have another question. Maybe Rizzo can take this one. So the question is from Imad. Is the cell needs any pressure to work? And how you are going to control it in the battery module?
So the cell, it's not that it needs pressure to work, it's more that during its lifetime, it will expand. Thank you. It will expand. So we need to ensure the contact and viable, to make the structure viable, we need to compress it to avoid the cells to expand too much. So this is already the case with liquid cell, but it's also the case with what we see it's also the case with solid state cells. So yes, it does need compression, and we as we said, we work with pressure sensors. So the goal is to see exactly how much pressure is built in this module. We don't have yet a communication with the mechanical compression. So the compression will not change during the lifetime, but it will be interesting to have this. And I think some projects do this, but in our case, the goal first of all is to measure the pressure during the lifetime, during the life cycle, and yes, to see actually if it would be needed to increase the pressure or not, or release some pressure during. But we do not here in this project.
Thank you so much, Bruno. I don't know if you have more questions. So I don't see any more questions on the chat, neither on the Q&A. So thank you everyone for joining us online, and special appreciation to all the speakers here at CA. So our collaboration is what drives Extended to make us design safer, lighter, scalable and sustainable semi-solid state battery systems. So we really appreciate AVESTA, CA, Flanders Make for being the faces of its workshop. So have a wonderful afternoon, and thank you again for joining us live here from CA. We look forward to seeing you in our next dissemination event. Please make sure you follow us on social media. Bye. Have a nice afternoon.